Alright, sup guys, welcome to today's show. So today we're going to talk about the GDT while developing our OS kernel. But in order to do that, you need to understand how the different operating modes of the Intel CPU works in the different stages, how to address memory basically. So the computer boots up in 16-bit real mode. So this is the same mode as the first x86 processor, the Intel 8088. So we can address a total of 1 megabyte of RAM. What we have is 5 hexadecimal digits, so it goes from 00000 all the way up to FFFFFF. And as you see, this is more than 16 bits, and the CPU registers are 16 bits. So we need to store this, the last 4 Fs somewhere, and this F somewhere. So let's say we want to write to F00080. Okay? How do we do that? So what we do is we move some value that we want to write. Let's say we move the byte into AL and we say that it's this, for instance. So we want to write this to this memory address. So first we need to take care of this F. And we do that by using the segment register. So we move this into DS, which is a data segment, and we put the F here and then 3 zeros like this. Then we do the actual write. So what we do is we move into DS the address that we want, so that is in this case 0080, and we want to move the value from AL. What this means is we will take the first F from the most significant niblet of the register, and we will add this to the target address. Okay, and then we make the write to this address. And it works similarly if we want to do a far jump to, I don't know, something like this, right? Then it works the same way, but it uses the CS register instead. So this is the old way of doing things in the Intel 8080. And we can only address 1 megabyte of RAM. Then we go to the next step, the one we are working in currently, which is 16-bit protected mode. And this is for the Intel 286 processor. So now we do it a little bit differently. We use the same instructions. So we move a byte into AL that we want to write, and let's say we want to write the same address as before, 0F0080. Make note that I add a 0 here, because in this operating mode we do not only go from 5 zeros to 5 Fs, we have 6 of them. So we go from all zeros, 6 of them, to 6 Fs, which lets us address 16 megabytes of RAM. But how do we do this? Move into AL80, and we want to do the write as before by moving a byte into DS 0x0080. So this does not change, and we want to write the AL value. But how we work with the segment registers do change. So last time we moved into ds, this address, right? But this time we moved something like an 8. So this is no longer used by calculating the address out of arithmetic. Instead, we use a table, the Global Descriptor Table, and there's also a local variant that we can use. And simplified, it has the following fields. So let's say we have an index first, which is not part of the table, but to make it a little bit easier to understand. Maybe we can even do this, right? And then we have a physical address. And then we have something called the limit, which is the size of that segment. And then some permissions, let's say. This is called the access byte, but let's say permissions. Alright, so what we do is the thing inside of the segment register, this 8 right here, we use that as an index into this table. And inside of here we define a segment that begins at address, let's see here, 0f 0000. So here we can specify all 6 hexadecimal digits, right? And then we have a size of that segment, and the maximum size is FF, which is 64K. And then we have some permissions, which basically says if we have read access or write access, and who has it? Is it ring 3, which is userland? Is it ring 0, which is a kernel, or both, etc.? So it basically says who can access this thing. And that's what makes it possible on a Intel 286 to actually write a multitasking operating system which is stable and secure. Alright, so why did I pick an 8 here? Well, this is maybe a little bit too detailed, but if we have 16 bits, so let's see, 4, 1, 2, 3, 4. Okay, so here we have all the 16 bits of the DS register. We are not using all of them, so these last 3 right here we don't use, because they are used for other stuff. So basically these are used to describe if we are accessing the global descriptor table or the local one, and also what access we need. So in this case, 000 means the global descriptor table, and it means this 0 right here means that we want to have kernel level access. Alright, so let's say we keep these 3 as 0, set one of them to 1, so this is the first thing inside of the table. Since we have a 1 here, well, there's a 0 as well, but that is not used because the 0 index is something which has zeros on all of them. and that's well, it's reserved basically. So a 1 here means that the first thing is 8, right? Because 1, 0, 0, 0 is 8. And that is what we put, why we put an 8 inside of this DS register. It has nothing to do with this entry in the table being 8 bytes or something like that, which basically every YouTuber seems to believe who talks about operating systems, but that's wrong. No. We are using this as an index, not as a byte by byte calculation. And this right here is the reason why we put an 8 here. Okay, so every time we want to address something in another segment, we need to load it into one of the registers, like DS or SS or CS. We have 4 of them. With Intel 286 semantics we do. And this means that how many can we put here? Well, since we have 13 bytes here to use as index, that means that we go to 81, let's see, 91 is the last entry, so we have 81, 92 entries. Let me just see that this is correct. Yes. And also each of these entries are 8 bytes because, well, the limit 16 bits, this is also 16, no, it's 20 bits, 24 bits even. Permissions is 1 byte, and then we have one reserved here, which is 16 bits of zeros. So total of 8 bytes per entry. And if we times 8192 by 8 bytes, we get 64K, which is the total size of a segment. So the Global Descriptor Table and its local variants takes up a maximum of 1 whole segment of memory. So this is what we want to create. So we need to create a memory manager which takes care of this table. So we'll have something like kalloc that we tell that we need, let's say, I'm not sure if I'm going to say 1 segment or if I need 64K or maybe some smaller variant. But what it will return is a descriptor. So something like 08, correct? That we can use and put inside of the DS register or any of them, and then we can allocate that thing. So it needs to take care of this table and take care of all the memory. And my current idea, I haven't settled on this 100%, but I think I'm gonna divide everything. So instead of using the maximum size of 64K, I want to have 32K. And then I want to have the ability to tell kalloc that we want a large segment. And in that case, we can use the whole 64. So I think I'm going to populate the entire thing, right? So if we use 32K, so the physical address will start at 6 zeros at index 1. Then the next one will go half a full segment. So a full segment would be, let's see here, a full segment would be something like this, -1. So this will be the next one then. But since we're using only half a segment, it's going to be, let's see here, half of this is a 7, no, an 8 here. Yeah, so this is index 2 then. Is that correct? So first we have this, then we have an 8 followed by, no, it should be like this, right? Because we have these 4 last digits to work with. So this will start at this address, and then the third is going to be 0, 1, 0, 0, 0, 0, and so on. So everything goes in 32K increments. And if we want to allocate a large segment, let's say. So let's say that this is taken. So that means that the present bit is 1. That means it's active, right? So we will start with p equal to 0 on everything. And let's say we have a fourth as well, which would be 0, 1, 8, 0, 0, 1, 8, 0, 0, 0. Okay, so let's say we call k alloc, and we say that we want 64K, right? So it will skip the first one because this is taken. And this is not big enough, and we don't want to start on an even, or do we want to start on an even number? Yeah, we probably do, which means that this we want to use. So basically we will delete this one. Maybe we can indicate that by putting a 0 here or something in here. And then we change this limit to 64K. We say p equal 1, and kmalloc is going to return 0x10 in this case, which is index number 2, because we do 8 hexadecimal jumps, and this is 16, right? And then we can use that segment. A lot of information, but I think it's important that you understand all of this stuff so we can start coding everything. Instead, we are going to use BIOS interrupt to fill up similar to this, only we don't need to use the data segment like this. Instead, we will have some other segment. Let's say, I don't know, this maybe. And let's say we have 30K for data for the kernel. And we have 32K as data for the drivers, because the kernel is going to be ring 0 and the drivers is going to be ring 2, and then we have the user land at ring 3. So that's a general idea. So if the user land wants to communicate with the drivers, it's going to have to do some system call. And I'm considering using ring 1 for the first level of system calls. This makes it for better security, I think. So we will validate the parameters, etc. at ring 1 and then kick it up to the drivers or to the kernel, depending on who is going to handle the request. But this will be all for today. If you like this episode, please like and subscribe, and we will continue this project in a later episode. Thanks for watching. Thanks for today.